Have you ever held a hot cup of coffee and wondered if it weighed more than when it was cold? It seems like a strange question, almost a trick. Our daily experience tells us that things don't change their weight just because their temperature changes. A rock is a rock, whether it's been under the summer sun or in a winter frost. But what if I told you that, deep within the fundamental laws of the universe, there's a hidden connection? What if heating something, adding energy to it, really does make it weigh more? It's a truth that defies our common sense, a secret whispered by the cosmos itself. The universe is often more subtle and interconnected than we imagine, and this simple question opens a door to understanding its deeper principles. The answer isn't a simple yes or no, it's a journey through the history of science. It takes us from the predictable mechanical universe of classical physics to the mind-bending realities revealed by Albert Einstein. We'll have to travel to the very heart of matter and energy to see how they are two sides of the same cosmic coin. This isn't just a fun fact for a trivia night, it's a profound insight into the essence of reality. The extra weight is so incredibly small, so fantastically tiny that you'd never notice it in your entire lifetime. And yet its existence is a cornerstone of modern physics, a testament to how our universe works on the grandest scales. So, let's embark on this adventure of the mind. Let's take that seemingly simple question and follow where it leads us. We'll explore the very definitions of what it means for something to have mass and weight. We'll see how old ideas were overthrown by a more complete and beautiful picture of the cosmos. We'll discover that the energy warming your hands on a cold day is fundamentally linked to the gravity that holds you to the Earth. The story of why hot objects weigh more is the story of how we came to understand the universe in a completely new way, revealing a hidden unity in the forces of nature. Get ready for your intuition to be challenged. The world we perceive with our senses is only one part of the complete reality. Science gives us the tools to see beyond those limitations, to grasp concepts that are both astonishing and deeply satisfying. That cup of coffee, that heated piece of metal, aren't just hotter. They are, in a very real and measurable sense, more massive. Let's find out why this seemingly impossible idea is not only true, but essential to our understanding of everything, from the smallest particles to the largest structures in the cosmos. The journey begins by using the right words, defining the tools we'll need to explore this amazing idea. Before we can dive deep, we must ensure we are speaking the same language. In science, words have very specific meanings. Let's start with mass. Think of mass as the amount of stuff in an object. It is a measure of an object's inertia, which is its resistance to being pushed. A bowling ball has much more mass than a tennis ball. It's harder to get the bowling ball moving, and it's harder to stop it once it does. Mass is an intrinsic property of an object. It doesn't change whether you are on Earth, the moon, or floating in the vast emptiness of space. It is the fundamental measure of the matter that makes you, you. Now let's talk about weight. Weight is a force. It is the force of gravity pulling on an object's mass. Your mass is the same everywhere, but your weight changes depending on where you are. On the moon, which has much less gravity than Earth, you would weigh only about 1/6 of what you weigh here, even though your mass, the amount of you, hasn't changed at all. So when we ask if a hot object weighs more, we are actually asking two things. Does its mass increase, and does that mass increase result in a stronger gravitational pull? The two concepts are intimately linked, and we must be careful not to confuse them on our journey. Next up is temperature. Temperature is a measure of the average kinetic energy of the atoms and molecules within an object. When you heat something, you are making its tiny constituent particles jiggle, vibrate, and move faster. A hot object is one where its atoms are vibrating with energy, whereas a cold object's atoms are much calmer and slower. This movement and jiggling is what we call internal energy or thermal energy, and heat is simply the transfer of this thermal energy from a hotter object to a colder one. It's important to remember that cold is not a substance. It's simply the absence of a large amount of thermal energy. So to recap our cosmic toolkit, mass is the amount of stuff. Weight is the force of gravity on that stuff. Temperature measures the average motion of the atoms in that stuff. And heat is the transfer of that motion energy. With these definitions firmly in hand, we are now equipped to travel back in time, to an era when the universe seemed a little simpler, a little more straightforward. We are heading to the world of classical physics, where mass and energy lived in separate homes and were not yet known to be family. This foundation will be crucial for appreciating the revolution that was about to come. Let's imagine the world as seen through the eyes of a 19th century physicist. This was the era of classical physics, a masterpiece of human intellect built by giants like Isaac Newton. From this viewpoint, the universe was a large, predictable machine, like a magnificent clockwork mechanism. Everything worked according to clear and distinct laws. Matter was matter and energy was energy. They were two completely separate and unrelated things. Matter had mass and was conserved. It could not be created or destroyed. Energy could change form, from chemical to kinetic to thermal, but the total amount of energy was also conserved. They were two parallel and unchanging pillars of reality. In this classical world, heating an object was a simple process. You simply added energy to it. This would increase its internal thermal energy, causing its atoms and molecules to vibrate with greater vigor. This explains why a hot piece of metal expands. Its agitated atoms need more room to move around. But, according to the laws of the time, this process had absolutely no effect on the object's mass. The amount of stuff in the object remained exactly the same. Adding energy was like adding a coat of paint. It might change the object's properties, but not its fundamental substance. So, its mass, and therefore its weight, would not change at all. Sometimes scientists in a lab might observe what looked like a change in weight. For example, a very sensitive scale might show that a hot object weighed slightly less than a cold one. But classical physicists had ready explanations for these observations, and they had nothing to do with a change in mass. The most common cause was air currents. A hot object heats the air around it. This hot air rises, creating a gentle updraft that pushes the object up, making it seem lighter. It's an illusion, an experimental artifact. Not a true change in weight, but a buoyant force from the surrounding air playing tricks on delicate measuring equipment. This worldview was incredibly successful. It allowed us to build steam engines, understand the orbits of planets, and develop technologies that transform society. The separation of mass and energy was a central assumption that worked perfectly for every experiment and every observation of the time. There was no reason to doubt it. The universe was orderly, its books were balanced, and the accounts of mass and energy were kept strictly separate. The idea that simply heating your dinner could make it infinitesimally heavier would have sounded like complete nonsense. But the 20th century was dawning, and a revolution was brewing in the mind of a young patent clerk. The dawn of the 20th century brought with it a huge change in how we understand the universe. In 1905, a young Albert Einstein published a series of papers that would forever change the world of physics. One of them showed the world what would become the most famous equation in history: E equals mc squared. This neat and simple-looking formula showed a deep and new connection between energy and mass. The CE in the equation is the speed of light, a very big number, and squaring it makes it even bigger. What this equation tells us is that mass is a type of energy, and energy has mass. This was a complete change from the old way of thinking. Mass and energy were no longer separate things, they were two different forms of the same basic thing. Mass could turn into a huge amount of energy, which is how nuclear power and atomic bombs work. But the equation works both ways. Energy can also turn into mass. This means that if you add any kind of energy to an object, you are also adding, by definition, a tiny bit of mass. Suddenly, the question of whether a hot object weighs more takes on a whole new meaning. The answer, according to Einstein, had to be yes. When you heat an object, you are increasing its inner heat energy. Its atoms and molecules are shaking with more force. This added energy, this buzz of inner activity, makes the object's total mass bigger. The object is now, in a very real way, heavier than it was when it was cold. The increase is super small because the conversion factor, the speed of light squared, is huge. You are dividing the added energy by a giant number to find the resulting mass. But no matter how tiny, the increase is real. It's a direct result of mass and energy being the same thing. This idea completely changed how we understand matter. An object's mass isn't just the total of the masses of its tiny parts, like protons and neutrons. It also includes the energy that holds those parts together and the energy of their movement. When you heat your coffee cup, the added heat energy becomes part of the coffee's total mass energy. So it becomes a little heavier and, as a result, weighs a little more. The old classical idea wasn't wrong, but it wasn't complete. It was a good guess for the world we see, but Einstein gave us a deeper, more exact way to describe reality. Einstein's discoveries didn't stop with special relativity and E equals mc squared. About a decade later, he unveiled his masterpiece, the theory of general relativity. This was a new theory of gravity, and frankly, it was even more groundbreaking. Newton saw gravity as a mysterious force acting at a distance between two objects. But Einstein showed us something much more beautiful. He proposed that mass and energy actually warp or curve the very fabric of space-time itself, the four-dimensional canvas of the universe. What we perceive as the force of gravity is actually just objects following the straightest possible path through this curved space-time, kind of like a marble rolling on a curved surface. General relativity deepens the connection between energy and gravity. It states that not only does mass curve space-time, all forms of energy and pressure contribute to this warping. This includes the kinetic energy of motion, the potential energy stored in a field, and, crucially for our question, the internal thermal energy of an object. So, when you heat an object, you're not just increasing its mass according to E equals mc squared, you're also directly contributing to its ability to warp the space-time around it. The object's gravitational influence on the universe becomes just a tiny bit stronger. This means the thermal energy in your hot cup of coffee is doing more than just making the water molecules jiggle. That vibrational energy is actively participating in the cosmic dance of gravity. It's contributing to the curvature of space-time in its immediate vicinity. Of course, the effect is tiny for something like a cup of coffee. The extra curvature is so subtle it's completely undetectable in our daily lives. But the principle is profound. It tells us that energy, in all its forms, is a source of gravity. The heat you feel from a fire is, in a physical sense, a source of gravitational attraction. So now we have two layers to our answer, both coming from Einstein. Special relativity tells us that the added thermal energy increases the object's mass, its inertia. General relativity tells us that this added mass energy increases the object's gravitational field by curving space-time more. The result is the same, the hot object weighs more. It's pulled more strongly by Earth's gravity, and in turn, it pulls on Earth more strongly. This unified picture, where energy and gravity are so intimately connected, is frankly, one of the greatest achievements of modern science. It reveals a universe far more interconnected than we ever suspected. Alright, we've established the principle. Adding heat adds mass and weight. But how much exactly? This is where the sheer scale of the universe really becomes clear. Let's take a practical example to see just how tiny this effect is. Imagine we have 1 kilogram of water, which is about a liter. We'll start it near freezing at 0 degrees Celsius and heat it up to its boiling point at 100 degrees Celsius. This requires adding a specific amount of energy, which in scientific terms is about 420,000 joules. That's a considerable amount of energy, enough to power a bright light bulb for over an hour. Now, let's use Einstein's famous equation E equals mc squared to figure out how much extra mass this energy adds. We need to rearrange the formula to solve for mass, m equals E divided by c squared. We have our energy, 420,000 joules. The speed of light, c, is an astounding 300 million meters per second. When we square that number, we get 90 quadrillion. So, we divide our 420,000 joules of energy by that astronomical number. The result is a mass increase of about 0.0000000000047 kilograms. That's 4.7 nanograms. It's an almost impossibly small amount. Let's try to visualize what 4.7 nanograms looks like. A single grain of sand has a mass of about 1 million nanograms. A human eyelash weighs a few thousand nanograms. The mass we've added to our kilogram of water by heating it to boiling is less than 1/100,000th the weight of a single eyelash. It's like adding an extra blade of grass to a vast, sprawling lawn. The original kilogram of water has a mass of 1 trillion nanograms. We've added less than 5 nanograms to it. The change is truly, fantastically, astonishingly tiny. That's why for all of human history, no one ever noticed this effect. Our most sensitive scales cannot detect such a minuscule change in an object weighing a full kilogram. Apparent weight changes due to things like air currents are millions of times larger than the actual mass change due to relativity. Classical physicists were right in a practical sense. For all earthly purposes, the weight change is zero. But in a fundamental sense, they were wrong. The change is not zero, and its existence points us toward a deeper, more accurate understanding of the laws governing our cosmos. Given that the increase in mass is so incredibly small, it's natural to wonder how we can be so sure it's real. Can we really measure it? The direct answer is no, not for an object like a coffee cup or an iron block. As we saw, the change in mass is too tiny to be detected even by the most sophisticated weighing instruments we have today. The noise from other factors such as vibrations, changes in air pressure, and the aforementioned air currents would completely overwhelm the tiny relativistic effect we're looking for. It's like trying to hear a pin drop in the middle of a rock concert. So, if we can't measure it directly on a scale, how do we know that E equals mc squared is correct? We know this because we see its consequences confirmed with astonishing precision in other areas of physics, particularly in the field of nuclear and particle physics. In particle accelerators, where tiny subatomic particles collide at nearly the speed of light, the conversion of energy into mass and mass into energy is not a subtle effect, it is the main event. New particles are created from the pure energy of the collision, and their masses perfectly match the predictions of E equals mc squared. Furthermore, nuclear reactions provide powerful and everyday proof. In a nuclear power plant, a small amount of mass from uranium atoms is converted into an enormous amount of energy, which we use to boil water and generate electricity. The amount of energy released corresponds exactly to the measured mass loss, which again confirms Einstein's equation. These experiments prove mass-energy equivalence under much more extreme conditions than simply heating water, and have verified it with an incredible degree of precision. We are confident that the principle applies to thermal energy because it has been shown to apply to all other forms of energy we can test. Therefore, our confidence does not come from weighing a hot brick. It comes from the overwhelming and consistent success of the theory of relativity in all other domains where it has been tested. The theory is a unique and coherent framework. If E equals mc squared is valid for nuclear reactions and particle collisions, it must also be valid for thermal energy in a hot liquid. The effect is real, even if it's too subtle for a direct demonstration in our kitchen. Science often works this way, confirming a broad principle in one area, and then applying its logical consequences to another, even when direct measurement is beyond our current technological reach. While the mass of heat is negligible in our daily lives, there are places in the universe where this effect is anything but small. We need to look to the stars. A star, like our sun, is a colossal nuclear furnace. In its core, unimaginable pressures and temperatures, millions of degrees Celsius, drive nuclear fusion. Hydrogen atoms fuse to form helium. During this process, a tiny fraction of the hydrogen's mass is directly converted into an enormous amount of energy, according to E equals mc squared. This is the energy that makes the star shine, bathing its planets with light and heat. This process has a fascinating consequence. The sun is constantly radiating this energy out into space, and because energy has mass, the sun is constantly losing mass. Every second, our sun converts approximately 4 million tons of its mass into energy. That sounds like a lot, and it is, but the sun is so enormous that it can keep doing this for billions of years. Over its entire lifetime, it will only lose a tiny fraction of its total mass. This continuous loss of mass energy is a direct, large-scale demonstration of the principle we've been discussing. The heat and light emanating from the sun have mass, and that mass is being subtracted from the sun itself. The weight of energy also plays a crucial role in the stability and evolution of stars. The immense thermal energy and pressure within a star's core actively contribute to its gravitational field. This energy helps to counteract the star's own crushing gravity, holding it up and preventing it from collapsing. When astronomers model a star's life cycle, from its birth in a nebula to its eventual death as a white dwarf or supernova, they must include the mass equivalent of its thermal energy in their calculations. For these cosmic giants, the weight of heat is not a trivial footnote, it is a key factor determining their fate. Looking even further back, to the very beginning of the universe, the concept becomes even more critical. In the first moments after the Big Bang, the universe was an incredibly hot, dense soup of energy and fundamental particles. There was almost no distinction between matter and energy. The universe was essentially a sea of pure energy, and its immense energy density was what drove the initial expansion of space-time. In this primordial state, the weight of heat was not just a factor, it was everything. The gravitational properties of the early universe were entirely dominated by its thermal energy content, shaping the cosmos we see today. So, we return to the beginning, to our simple cup of hot coffee. Does it weigh more than when it's cold? The answer is a resounding yes. The journey to that answer has taken us through the fundamentals of physics. From Newton's mechanical universe to Einstein's revolutionary space-time, We've had to redefine our basic concepts of mass, energy, and gravity. We've seen that mass and energy are two sides of the same coin, united by science's most famous equation. A hot object is more energetic, and therefore is more massive, and therefore weighs more. The change in weight is real, but it's also fantastically, almost comically, small. It's such a tiny change that it stays hidden from our human senses, buried under the noise of our everyday world. We could live 1,000 lives, and never build a scale sensitive enough to detect the extra weight of a hot object in our kitchen. In our daily experience, the old way of thinking still holds true, but that doesn't make the hidden truth any less important. The reality of the universe is often found in these subtle effects that hide just beyond what we can easily see. The importance of this idea isn't in how we use it every day on Earth, but in what it tells us about the basic rules of the universe. It shows us a graceful and connected cosmos, where the energy that warms us is a source of the gravity that keeps us on the ground. This principle, so tiny in a cup of coffee, becomes a powerful force when we talk about stars and the whole universe. It's key to understanding how stars shine, how they live and die, and how the universe itself grew from a hot, dense point to the huge starry space we see today. So the next time you hold a hot object, take a moment to appreciate the hidden physics at play. That heat, that movement of atoms, is adding a tiny, unnoticeable amount of mass to the object in your hands. You are holding a direct result of Einstein's theory of relativity. You are seeing a basic rule that guides how the entire universe works, from the smallest particles to the biggest galaxies. The universe is full of these beautiful, hidden connections, waiting for a curious mind to ask a simple question and follow the answer wherever it leads.